should I do now? Okay, so now you start recording. I hit it. طيب. So since the beginning of this semester, we talked about the first part of material science, which is the structure of the material, right? Remember in the beginning, we said we have two tasks. Number one, we want to know more about the structure. And then the second task, we will get into the second task where we will talk about the properties, the behavior of the material. Because we said earlier, and if we can tune the structure or understand the structure, we can explain a certain behavior, certain properties of the material. Okay, so the first 6 chapters that we talked about so far, we only try to understand what are the possible
يتقطع عندكم ولا أنا الحالي؟
حتى أنا
ما قطع
الصوت.
شو؟
قطع الصوت دكتور.
Okay. طيب. Okay, do you now hear me well? Do you hear me now well?
إيه الحين كويس.
طيب. So what I was trying to say, إنه materials will have different properties according to their structure. So in chapter 2, 3, 4, 6, we try to understand, and 7, we try to understand more about the structure, right? So we were able to classify them and to see what are the different possible structuring of the material. Now today we will start the new task. We will try to see how the material behave. Okay, what are the we talk about the properties of the material. And since this course is offered under the mechanical engineering department, we'll be more focusing on the mechanical behavior of the material. Okay, so in this course we will not talk about the electrical properties or the optical properties or magnetical properties of material. But we will be focusing on the mechanical behavior of the material. Great. So what I want you to do, I want you to go to the first example. The first example in this chapter. The chapter is called Mechanical Properties of Metals. So I want you to go to the first example and highlight and underline the main or the new words in that example. Okay. So this is the example over here. Okay. You see it now? You see it clearly? Do you see the example?
Yes.
Okay. Do like this and then. Okay. Wonderful. So now let's highlight and underline some words. Okay. Can you tell me some new words that this is the first time for you to read it, or a main word or keyword that you would like me to talk more about it?
Yalla. Elongation.
Elongation. Wonderful. Elongation. Okay. What else?
Deformation.
Deformation.
Tension.
Sorry?
Tension.
Tension. Yes, tension. Wonderful. So tension. What else?
Entirely elastic.
Entirely elastic. What else?
Stress.
Yes, yes, salam. Wonderful. So stress. What do you think? I don't see a strain here. Fair strain.
No, I jumped to the solution.
No, only look at the question here. Okay. So, what do you think the question is talking about? Before we start explaining the chapter, what do you think this chapter or this question is talking about?
About the extension.
Sorry?
Maybe. About the extension.
Extension. Okay. Extension. Okay. So extension. That means how much additional or variation happening to the dimension of the material. طيب. What else?
يتكلم عن التشوه اللي يصير للمادة بعد ما نحط عليها فورس.
Okay, wonderful. So this question is saying you have a certain material and you are exposing it to a certain environment, and that environment will trigger some behavior or specific type of behavior from the material, right? So you're applying that environment in a certain environment, okay? And that environment results in a certain something, okay? Why do you think I highlighted these two words in green and the other words in yellow?
ممكن affect و result يمكن. Affect و result يمكن.
Okay, cause and effect. Okay, wonderful. Yes.
The relation between them, I think.
Okay, relation between them. Wonderful.
Maybe categorize them.
So you see the green word here is representing what are we doing to the material, what kind of environment the material is exposed to. And the other color is telling you something about the response, how the material is responding, right? Right, if the material, so the yellow color is telling you the material is responding in a certain behavior according to certain environment. Okay, wonderful. What does the word entirely imply? What does the word entirely imply? Entirely is entirely something. So the deformation is entirely something.
During the whole process?
During the whole process is elastic. Okay, wonderful. What else? What does word imply?
Fully.
Huh?
Like fully elastic.
Fully. Okay. Very good. So fully entirely elastic.
Also,
completely.
What?
In all parts of the metal.
Okay, one by one. Let's go to Ahmed Bahjan. Bashhan.
Yes, معناها كليا.
Okay, so what does that imply? ماذا هذا يعني ايش هذا الشيء يقتضي؟ يقول لك deformation
مؤقت بعد ما تشيل الفورس راح ترجع لوضعها الطبيعي.
Okay.
Reacting in the same way.
Okay. What else?
The entire volume of the piece of copper.
Entire, okay. So deformation is entirely elastic. من إجاباتكم from your answers, you're saying إنه whatever deformation is happening in the material is elastic deformation. I got it. Do you think this also implies something else when you say deformation is entirely elastic?
There is no other type of deformation other than...
Yes, salam, wonderful. That means possibly material can have other type of deformation, but in this case, we will only have one type of deformation, which is elastic deformation. Right? معناته we might have different types of deformation. Okay? And the first one is called elastic deformation. The second type, it's called plastic deformation. Okay, so plastic deformation. What do you think the difference between elastic and plastic?
There's no coming back from the plastic one.
Oh, okay. So there is no the material will not get back to its original dimension if the material is exposed to a certain type of deformation. It's called plastic deformation. صح? So the difference between elastic and plastic is elastic, when a material is elastically deformed, the deformation will be temporary there. Once you remove the material from that environment, let's say once you remove the material, if you apply a force, the material elastically deformed, once you remove your hand, okay, everything gonna get back to its original dimension. right? This is elastic deformation. So elastic deformation, things will get back to its original dimension. Plastic deformation, it's a permanent deformation. تشوه دائم. Things will not get back to original, right? So now we have two types of deformation. One is elastic, the other one is plastic. And in this case, in this example, it's saying that it's entirely elastic. That means whatever deformation is happening, it will be deleted, shift deleted, you know, once you remove the environment. It will get back to its original dimension. Okay? Wonderful. So both deformation, okay, let me say that very clearly. Both deformation, the elastic and the plastic, will result into elongation or deformation, but the difference here is that the elastic is temporary there, okay? The plastic will be permanently there, okay? Okay, great. So now the first part here is that we now can distinguish between two different types of deformation. Wonderful. Now let's dig deeper into the elastic deformation. Let's dig deeper into the elastic deformation. Now, elastic deformation, we agreed that if you apply a certain force into the material and you remove your hand, you remove that load or that force, what's going to happen? The material will get back to its original dimension. But some material, yes, it will get back to its original dimension, but it needs some time. This is why some material, okay, will have time-dependent elastic behavior, and that's called anelasticity. So the material will get back to its original dimension, but it needs some time. It will not get back to its original dimension all of a sudden once you remove your force, okay? It needs some time. Wonderful. But what else? Well, let's dig deeper into this example. Why the question is saying pulled in tension? Why did the question not say the sample was exposed to a force and that's it? Why do you think he specifically, or let's say he or she specifically said intention? Why?
انه نفس الاولى يمكن في تاج ثاني
لان لو قال compression راح يقل الطول، اما tension معناتها راح يكون في اطاله.
Right. So, in other words, the material can be exposed to different types of forces in real applications. That could be tension, right? Tension, where you have, this is your sample, okay? This is your sample, okay? And then what you do, you apply a uniaxial force that is perpendicular to a certain area, right? That's called tension. That's called tensile force. You're applying a tensile force, okay? But also you can apply different types of force. Let's say you have the same cylinder, okay? Okay, and you apply different types of forces, okay? And that force is in the opposite direction. So this one is called compression, and this one is called tension. So what do you expect here? You expect at the end of the day, the sample will be elongated. You have additional length, okay? Additional length in the direction of the applied force. Here, you're expecting to have some shrinking, right? In the dimension that is in the direction of the applied force, okay? What other type of forces the material can expose to? Okay, imagine you got something like this, okay? What do you think the difference is here? Okay, what do you think if you apply this kind of force that is parallel to the surface, that result in what? That result in what?
Stress.
That's what it is. Okay. What do you think the relation between these kind of forces in this example, okay, and this case?
This is a shear tension.
What do you think the relation between this force and the area in these two examples and this example?
الثانية على السيرفس
Okay.
يمكن تأثر في السيرفس.
الثانية. Okay. So in the first two examples, the forces are normal to the cross-sectional area. And here the force is parallel to the cross-sectional area, right? So this called, you have a shear stress here, okay? That might result in shear, you're applying a shear, okay? Or also can have something called torsion, right? So the material can expose to tension or compression or shear or torsion. There are different types of forces. And I would urge you to go to examine a figure, the first figure in this chapter, where it's illustrating different possible type of forces the material can expose to. Okay, so when the question is saying pulled in tension, that means we are dealing with which case? We are dealing with this case, right? So the material being exposed to a force that is normal to a certain area, right? Okay, and that will result in elongation in that region and in that sample, in that direction. Okay, hello. This is what we mean by tension. What do we mean by stress? Why the question did not say with a tensile force? Why he specifically or she specifically said stress?
No, it's normal to the cross section.
Okay.
It is 90 degree.
What do you think? What else?
I think because the stress is related to the change in the area.
Okay. Okay, let's deal with these two examples. Imagine we are applying the same amount of forces. For these two, and we want to compare their mechanical behavior. We want to say we want to see which one is, let's say, more stiff. We're going to talk about what does stiff mean. In other words, let's say which one more stronger. Okay, we cannot compare between the two because the two they have different dimension. For the side, they have different cross-section area. So if you're applying, let's say, 30 Newton, that 30 Newton will be translated into different values because you have different area here, right? This is why typically we use what? We use what's called stress. Stress معناته we are normalizing the force, right? By dividing it over the area, the original area, okay? So we are saying whatever force you're applying, divide by the area. Then, if you go to the lab and you want to compare the mechanical behavior of two samples, you will say, I'm going to apply, let's say, 80 megapascal, okay? And that will be a fair treatment to both samples because you're considering the dimension. Okay, so stress عبارة عن force over area. But why I said original area? Why I specifically said original area?
لأنه القطر حيفرق.
Okay, wonderful. Because we expect let's say, okay, let me now delete this. Let me delete this. Okay, let me delete it. And now let me draw something else. Let's say you have, this is your sample. Oh, let me have something. Okay. Let's say this is your sample. Okay, wonderful. So you have a cylinder with a certain dimension. And then you start to apply a tensile force, Okay, what do you expect gonna happen to the material, to the sample?
القطر حيقل حق الاريا حتقل بشكل عام.
Okay,
والهايت حيرتفع.
Wonderful.
وفي الكمبرس حيكون الاختلاف العكس.
Right. Because we have a constant number of atoms. We are not adding atoms to the material. We are not taking atoms out of the material. So if the material has to elongate in a certain direction, right? What does that mean? That means the atoms from the side should serve the new mission for the materials to elongate in a certain direction, right? So what's going to happen? Well, the material will elongate, it will have now more length in the direction of the force, but at the same time, okay, this is not, okay, let's try it one more time, okay. Oh, alhamdulillah, okay, almost there, huh? Assume there's a straight line, okay. Now the material will have smaller area, and longer length, wonderful. But as we're calculating the stress, we are dividing by the original area, which is wrong because as we're applying the force, the area is shrinking, right? So in the best way, or let's say the true way of doing it, we should divide the force by what?
The change of area.
Hello. Okay, the change in area. Let's use other words. We should, in order to calculate the stress, we have to divide the force by
delta.
Okay, what else?
The original area.
Original area, original area. This is called, so here you divide force over original area. But this is not the correct way because you know the area is changing. Could change. The area could change.
in function of t, Doctor.
Function of t. Let me know if you like this. What about if you say force over an instantaneous area? An instantaneous area اللحظية والآنية. You like it?
Yes, same.
Differentiation. So that would be more representative, accurate representation of the stress. Right? So this should be A over the instantaneous area. Right? طيب. Now, let me tell you something. This shouldn't be, we shouldn't use this, huh? But we will be using it. Until the end of this chapter, then we're going to tell you this is not correct. We're going to use something else, right? Now, the one to the left, it's called engineering stress. Engineering stress. Okay? And at the end of the chapter, we'll tell you, look, there is something called true stress, and there is something called corrected stress. Right? But someone can ask a question, why we are studying something that is not, true and not corrected, right? Because it turned out it might be difficult to measure what's happening at the cross-sectional area, the changes that are happening. Right? So what we will do, we will close our eyes. We will say, well, nothing's happening to the cross-sectional area, and then at the end, we will be using some equations, okay? Some equations that will convert the engineering stress to the true stress or corrected stress. Got it? In other words, engineering stress will be used, and then to get this, we will be using some equation to convert this value to this value without the need of doing some measurement in the lab. Okay. Also, in some deformation, there will be not that much changing happening in the area. Right? So that means this will work fine. Actually, not fine. Will work perfect because there's no change happening. No any changes happening in the cross-sectional area. So we are good. Or let's say the change is very, 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 very minimal. Right? So it's not something significant to consider, right? So that equation will work fine. And once you get into the region where the changes in the area is significant, okay, we'll still divide by the original area, but then we will use some equation to convert that value to the true value. Is it clear, Shabab? Okay, is it clear?
Yes.
Okay, wonderful, great. طيب, now then let me delete this, and we will we'll talk about the true stress and the correct stress later in this chapter. Now we'll focus on engineering stress. So wonderful. So now engineering stress equals to force over area, the original area. Okay. And since we are talking about tensile or tension stresses, we're talking about force that is normal to this area, right? Okay. What else? Now, we said that we have elastic deformation and also we have plastic deformation, right? So that deformation will be translated into some changing, some changes in the dimension, right? That could be elongation, that could be shrinking, right? And in order to quantify this, we will be using something called strain, okay? Strain, which is delta L over the original length. Also, this one is called engineering strain. As we go at the end of this chapter, we will talk about true strain, and also we'll be talking about we'll talk about the true strain, right? In the time being, we're going to deal with this engineering strain and engineering stress. Now, for the engineering strain, what do you think the unit will be? Do you think the unit will be in millimeter or nanometer?
Millimeter.
2D units less.
Millimeter. It's a wrong answer. طيب. What else?
No unit.
No unit, right? Because this is delta L. Let's say 5 millimeter minus 2 millimeter over 2 millimeter. That will give you unitless. So strain is unitless. Okay, great. Now this will be what we are applying, and this will be the response. Right? This is how we're going to quantify the response of the material by looking at the strain. Right? And this is what we are applying. Right? So in other words, this will stimulate this response. The stress will stimulate تستحث المادة إنها to change its dimension, and that will be quantified by using the strain. Because this is why in this chapter we will be dealing with what's called stress-strain curve. Stress-strain curve. Okay. So in the stress-strain curve, you got the stress, you got the strain. And what we will do, we apply a certain stress and we will see how the material will behave. And how the material will behave will be in terms of the changing in the dimension. Okay, great. Strain curve, typically it looks like something like this. Okay? Something like this. Do you hear me now well? Do you hear me well? Shabab, do you hear me well?
Yes.
Yes.
Okay. So this is called stress-strain curve. At this point, the sample, okay, will break. It's called fracture point. Now, do you think as you're applying the stresses, do you think first we will, in other words, which type of deformation you think it needs higher stresses? The elastic deformation or plastic deformation?
Plastic.
Plastic deformation. The one that has the one that has permanent deformation, right? And divide this curve into two regions. Okay, the first region is called elastic region, and the second region it's called plastic region. Okay, let's call this one plastic region. Now, there's a certain threshold with a certain stress. If you apply more than that stress, right, more than this value, you will get into the plastic region. If you apply below that stress, you will be in the elastic region. Okay? So if you apply stress more than this value, okay? If you apply a stress more than this value, okay? I don't like this one. Let me delete again. Oh, okay. So if you apply a stress that is more than this value, what you will have, if you apply a stress more than value, you will get the plastic region. You will get in the plastic region. If you apply lower stresses, you will be in the elastic region, right? Okay, great. So that means we have two types of stresses, two types of deformation: plastic deformation and elastic deformation. There is a certain point, a certain value of stresses. If you apply more than stress, you will get into the plastic deformation. For example, if you are designing, let's say, the cable that is holding the elevator, okay? Do you want that cable to get into the plastic deformation, or you want to make sure that whatever load inside that room will be less than that stress to be in the elastic region? So you want to be in the plastic or elastic?
In the elastic.
And the elastic, right? You don't want that rope to change its dimension every time someone is riding that elevator, right? So that stress is very important value that we need to identify, and we need to know how can we find that value for different material. Okay, what else? Also, we want to know how the material will behave during or inside the elastic region, because we just said, and the material will behave in this region elastically. If you zoom in here, okay, let's come here. If you zoom in, you will find that in the elastic region, the relation between stress and strain is linear relationship. It has a linear relationship. So if it's linear, that means it has a slope, and that slope will determine how easily or difficult we can elastically deform the material. Okay? So do you think if I compare this curve, let's call it A, with this curve, let's call B, which one you think it's easier to elastically deform it? Yalla, think for 10 seconds, and then I'm gonna get some answer from you. Which one is easier to elastically deform, A or B? Okay, think for 10 seconds. Okay, think for 10 seconds, and then I'm gonna get some answers. I will start with Usama Al-Asiri, okay? Okay, Usama Al-Asiri?
Yes, doctor.
So which one you think it's easier to elastically deform it? Material A or B? Usama?
Yes. Actually, I don't know it.
Okay, ممتاز. Let me walk you through how you can think about this problem. طيب. ايش يعني elastic deformation؟ معناته we are applying something to let the material elastically deform, to change its dimension. صح ولا لا؟
Yes.
بالتالي now let's say you're gonna pick this value here, okay, this stress. And then you hit this curve for B, and then you're going to go to the x-axis. Why are you going to go to the x-axis? Because x-axis is representing the strain. And the strain is delta L over L. How much changes we have for the length over the original length. Okay? So you think which one will have more elongation? Material A or B with the same amount of stress?
A.
Right, wonderful. A. So that means A, because it has different slope than B. B has a steep slope, right? So A has different slope. If you apply the same stress, you will have more elongation, more deformation in material A compared to B, right? In B, if you apply the same stress, you will get small deformation. Is it clear, Osama?
Yes, clear.
Okay, great. So what else we want to say here? So we will try to learn about the equations that govern this region, the elastic region, and also the plastic region. What is the threshold force or stress that if you apply more than that stress, you will get to the plastic region. Also, we will learn why the materials start to behave plastically. It was behaving elastically. Why it start to behave plastically? Okay, and the beauty of material science that we will correlate between the external behavior with the atomic behavior. Okay, so we're going to correlate whatever we see from macroscopic point of view with the microscopic point of view. Okay, we'll see how we can correlate between the atom's behavior, okay, with the changes that we see in terms of dimension. Okay, this will be the topic of discussion next lecture. So I'll stop here. I will see if you have any question.